In this lecture, we'll explore databases and SQL. Whether you're a comedian, or a lawyer, or a janitor, or a doctor, or a software engineer, we all encounter databases in the day-to-day world. We all use databases as well. So what's a database? It's a way to store information. A database is like a file cabinet or a chest of drawers in your bedroom where you store things. In the digital world, it's where you store data. There are different types of databases. For our context, we will focus on SQL and NoSQL. The SQL databases typically store relational data in different tables, and they're used for transactions and analytics and so on. The non-SQL databases are large stores of data where you can store petabytes of data. Usually these are in a key value pair, a column family, a graph, or in a document store type storage. In addition to that, we can categorize the databases as relational, operational, warehouses, distributed, and end-user databases. Relational databases are the most common ones. This is where you have different tables and there is a key for each table, and the tables are related to one another, and the examples of those include Oracle, Sybase, Microsoft SQL Server, MySQL, and so on. The operational databases are what typically organizations use to store large amounts of important data. So this data includes inventory, transactions, financials, customer data, products, purchases, and so on. The data stored in the operational databases can be changed and manipulated depending on what the company requires. Then you have data warehouses. The organizations need to keep large amounts of data in archives in order for compliance and other reasons like analysis and for data science and so on. So for that, they use data warehouses, for example, BigQuery, where you can store terabytes of data and you can run SQL queries on it. It's also used for ETL type jobs, extract, transform, and load. And most of that is done with SQL. And while you're transferring data between different databases or from an operational database to a data warehouse, then you have distributed databases. So this is where if you have organizations in different countries or in different cities, and they all need to share a database or be able to share data, then they can use distributed databases or have a database in the cloud so different people can access the same data. And finally, you have end user databases. So these are databases that are on your workstation or on your smartphone. For example, your mail app uses a SQL-like database and uses SQL language to actually fetch the results and so on, depending on the app that you're using. Now, a DBMS, a database management system, is a software system that enables users to define, create, maintain, and control access to a database or multiple databases. This provides data storage, retrieval, and the ability to update the database and the underlying tables. The database has an application that's used for running all these tasks, and that's usually called the database engine. And most of these DBMS also provide a public API that you can use to manipulate the data and the database management as well. So this allows applications to interact with the database and not just individuals. Some of the core features that these DBMS provide are the ability to store data, retrieve, and update, obviously, and also support for transactions and concurrency, provide users the ability to catalog or provide a data dictionary for metadata, provide facilities for recovering a database in case it gets damaged, and provide a high availability type solution or be able to replicate, support for authorization of access and the update of data, provide security, and provide support for remote connections and remote locations. So the most popular commercial databases are Oracle, Microsoft SQL Server, and DB2. And the most popular open source databases are MySQL, Postgres, MongoDB, Redis, MariaDB, Elasticsearch, Cassandra, SQLite, and ClickHouse. So Oracle is the most popular commercial database, and MySQL is also owned by Oracle. So Oracle owns both those number one positions. Now, traditionally, these databases would be installed on a server in a server room for a company. Now, there are mainly three additional options. Cloud service providers like AWS and Google Cloud Platform let you create and manage virtual machines in the cloud. You can install and run these databases on these virtual machines in the cloud. Number two, you can use containers. Docker images are available for the popular systems, and you can use Kubernetes, which is a container orchestration system, to manage the containers in the cloud. Finally, number three, you can use a managed service like Cloud SQL in Google Cloud Platform, or its equivalent in AWS, or even DigitalOcean. So there are a lot of benefits of using a managed service. It's a lot more easier to manage because all the infrastructure is taken care of. You can connect with different applications that are built for MySQL, Postgres, or SQL Server from around the world. They automate the database provisioning, storage capacity management, and other high time-consuming tasks. They also have on-site engineers working around the clock in case there are any issues with the infrastructure or if there are any servers that go down and so on. They also offer a high availability solution, provide backups, and security updates. So you don't have to worry about patches and updates as well because those are all taken care of for you. There's also easy integration with workstations because you can spin up other virtual machines and other products and services and then integrate them with your database in a virtual network. There's also security from infrastructure because all of this is done at scale. So the cloud service providers are managing hundreds or thousands of other clients. So security is important for them, and that security is scaled for the entire operation. Azure SQL Database is a fully managed platform by Microsoft and provides a service, platform as a service database engine that handles most of the database management functions like upgrading, patching, backups, and monitoring without any user involvement. The Azure SQL Database deployment model provides different versions. For example, you can install it as a single database, as a managed instance, or in an elastic pool. So a single database is just one fully managed isolated database. A managed instance is a fully managed instance of Microsoft SQL Server database engine. And the elastic pool is a collection of single databases with a shared set of resources like CPU or memory, and each database can be moved into and out of an elastic pool. In Google Cloud, there are a laundry list of different options here, and there are a whole bunch of at least 7 to 10 different types of databases that you can spin up, and they all have different parameters and different functions and different features and so on, depending on what's most important for you and what the purpose of the type of database you need and the type of data that you want to store. Now, an RDBMS is a relational database management system. This model organizes data into one or more tables or relations of columns and rows with a unique key identifying each row. So the rows are called records or tuples, and the columns are called attributes. Generally, each table and relation represents one entity type, like a customer or a product, and the rows represent instances of that same type, and the columns represent values attributed to that instance. So here we can see that in a diagram, and the reason for these tedious names is because there are many different types of databases in RDBMS, and they also can call their storage units rows and columns. So for example, in HBase or a big table type database, you also have rows and columns, but then you also have row keys and column families, and the data is organized in a three-dimensional way where time series data is stored in each cell. So that can still be called a row and a column, but in this case, when we say a tuple and an attribute and the relationship between them, then we know that we're talking about relational databases. Now, a primary key is a special type of constraint, and it's a column in the database that's unique, and it helps provide the identity for a table. No two rows can have the same value, and each row must have a value, so you can't have any empty cells in the primary key column. The primary key values can never be reused, and if a row is deleted from the table, then you can't reuse that same primary key value either. And likewise, you have foreign keys. A foreign key is the column in a table whose value corresponds to a primary key in another table. Now, this is how relationships are built in the relational database model. These foreign keys are extremely an important part of ensuring the referential integrity. So here in the example, you have two tables. You have the table departments and you have the table employees. So the employees table contains the data for different employees, and the departments table contains different departments that exist in the company. So in the employees table, you have a department ID that's being used as a foreign key with the name department number, instead of actually putting in the department name directly into that employees table. So the primary key for the employees table is the ID with the 100, 101, 102, and 103, and the primary key for the departments table is 10, 20, 30, and 40. Now, Ted Codd is the person who actually invented this relational database model. He came up with actually 12 different rules. So if a DBMS is designed as a relational database, then it generally has certain characteristics like we talked about, like the ability to store data in tables, and these tables must have a relationship, and so on. But these Codd's 12 rules were established to specify a set of criteria that could be used to determine if a DBMS could be considered a relational or not. So if a DBMS complied with all of Codd's rules, then it could be considered as a relational database and an RDBMS. Otherwise, it shouldn't. So let's look at what these rules are. So rule number 1 is the information rule. So here all the data, including the metadata, should be stored in tables and cells. And the rows and columns should be strictly unordered. Rule number 2 is guaranteed access. So each unique piece of data, the atomic value, should be accessible by table name plus primary key plus the attribute. So if you're using a pointer to access data, then that's a violation of this rule. The rule number 3 is how nulls are treated. So nulls have different meanings, and null just means that it's an absence of data. Active online catalog. So the database dictionary, which is the catalog, is a structure that describes the complete database, and it must be stored online. That catalog must be governed by the same rules as the rest of the database. Powerful and well-structured language. So there has to be a well-structured language that provides access to the data to store, manipulate, and so on. And that's, for example, SQL, which is what we'll be talking about here. The view updation rule. So all the views that are theoretically updatable should be updatable by the system as well. Relational level operation. There must be insert, delete, update operations at each level of relations. The set operations like union, intersection, and minus should also be supported. Rule number 8 is the physical data independence. The physical storage of the data should not matter to the system. Rule number 9, the logical data independence. So here, if there is a change in the logical structure, like the table structure of the database, the user view of data should not change. So for example, if a table is split into two tables, then a new view should give result as the join of these two tables. Integrity independence. The database should be able to enforce its own integrity rather than using other programs. So the key and check constraints, triggers, and all these are part of this. And all of these should be stored in the data dictionary. Distribution independence. A database should work properly regardless of its distribution across a network. So even if a database is geographically distributed with data stored in different pieces, then the end user should not know that difference. And then rule number 12, the non-subversion rule. If a relational system has a low level, like a single record at a time language, that low level cannot be used to subvert or bypass the integrity rules and constraints that are expressed in the higher level relational language. Now, these rules were written in an attempt to preserve the original vision of the relational model by Card himself. But the problem is that the relational model was created in the 70s and all these rules came out in the 80s. So by then, a lot of the vendors have already created database systems and they were already calling them RDBMS, although they weren't following all of these rules. So that's why he looks a little angry here in the picture, and that's sort of a meme on the internet as well. There are cartoons made of this that say that Ted Card still hates that thing that you just did because you didn't follow one of those rules. So even the most popular database like Oracle only follows, I think, around 8 rules. Database normalization. Normalization is a process of structuring a relational database in accordance with a series of so-called normal forms in order to reduce the data redundancy and improve the data integrity. So this was first proposed by Card himself and as part of the relational model. The normalization entails organizing the columns and the tables of the database to ensure that these dependencies are properly enforced and they're pure. These relationships should also be following the integrity constraints, and this can be accomplished by applying some formal rules, either by process of synthesis or decomposition. There are different normal forms, and the first, second, and third are the most important ones. So these are the ones that describe the way that primary keys and foreign keys and how they should be related, and how you can reduce the duplication of the number of rows by splitting the data into multiple tables. And there are a lot of different steps that you can follow in order to go from the first form to all the way to the 6NF, to the sixth normal form, if you wish to do so. Now, this is not a database course, so we're not going to talk about that in detail here. Now, SQL is a set-based declarative programming language that's designed specifically to query data that's contained in a relational database. So that's what it was invented for. And in computer science, a declarative programming means that it expresses the logic of computation without describing its control flow. So in other words, we know what it's supposed to do, but not know how it's doing it. This is also called a DS language, a domain-specific language, and that's what a domain-specific language is, something that specializes to a particular application domain, which is in contrast to a general purpose language, a GPL, which is broadly applicable across different domains. And as we discussed, SQL was invented by Donald B. Chamberlain and Raymond F. Boyce based on the Ted Cord's model, and this was developed at IBM. Initially, this was called SQL, SEQUEL, and it was designed to manipulate and retrieve data that's stored in IBM's original database system, which was the System R. There are extensions to the standard SQL, which add procedural programming language functionality and other constructs. For example, in the past, it was Fortran, Algol, COBOL, BASIC, Pascal, and C. So there are extensions to those that you can use to manipulate the standard SQL. And we also still have the Postgres SQL, which is also a programming language, which you can also use for procedural programming in addition to doing SQL queries. A little bit of history here. SQL was adopted as a standard by the American National Standards Institute, the ANSI, in 1986 as SQL 86. And then SQL was adopted as a standard by the ISO in 1987. The procedural and object-oriented programmability is available on many of the SQL platforms via the DBMS integration with other languages, like we just discussed, and the SQL standard defines the SQL JRT extension, the SQL routines and types for the Java programming language in order to support the Java code in SQL databases. The Microsoft SQL Server 2005 uses the SQL CLR, the Common Language Runtime, to host managed .NET assemblies in the database, while prior versions of SQL Server were restricted to unmanaged extended stored procedures, which are primarily written in C. PostgreSQL lets you write functions in a wide variety of languages, including Perl, Python, TCL, JavaScript, and C. The SQL 89 or the SQL 1 was actually a pretty useless standard because they just basically looked at all the available RDBMS and they just set up some standards based on those without actually having any implementation details or any of the numerous features that were supposed to be part of a standard. Then SQL 92 was the actual first solid standard of SQL by ANSI, and it provided some intermediate level conformance and some major improvements, like, for example, being able to name constraints, different length characters, dynamic SQL, and the ability to use set operators, updatable views, and so on. SQL 3, which is the SQL 99, that's the actual major SQL standards. So this was actually almost 2,000 pages long compared to 120 pages for the 89. So this also provided the different details for vendor-specific extensions and object-oriented programming, as well as the description of what the relational and non-relational databases should or shouldn't have. SQL 3 extends the traditional relational data models as well to incorporate objects and complex data types within the relational tables and also support for these mechanisms. It also brings into SQL all the major object-oriented programming principles like inheritance, encapsulations, and polymorphism. So the rest of the standards are just mostly incremental, and different companies and different systems use different variations of SQL. Like, for example, the Microsoft SQL Server uses something called T-SQL, and IBM uses SQL-PL, SPL, and so on. And Oracle uses something called PL-SQL. And also, for example, if you're using the MySQL, which is the open source database system, then there are a lot of different functionality and syntax that may or may not be compatible if you're using Microsoft SQL Server or Oracle and so on. So this is why you need to check and see which system you're operating on because SQL just stands for Structured Query Language. Now, SQL has three sub-languages: DML, DDL, and DCL. The data control language, DCL, controls user access to the database and does not use any predicates. The DML, which is the data manipulation language, is where users can ask queries like select statements or make changes to the data using the insert into, update, and delete from statements. The data declaration language, or the DDL, is where the administrators can control the schema objects like tables, views, stored procedures, and so on. Now, here are some real world examples. So, most of the databases now that you might encounter in the real world are going to be in the cloud. So, you're not really going to see too many of these data centers or server rooms. Rather, you will, of course, see a lot of data centers. And there are still a lot of companies that are using their own private cloud or their own on-prem system, and then using a hybrid solution with a cloud provider or set up their own cloud system. So here we can see an example of an architecture for one market. This is a data analytics company that provides insights into retails. So malls with thousands of stores, and they have a lot more, like tens of thousands of customers. The One Market team employs a microservices architecture to develop, deploy, and update parts of their platform quickly and safely, and each microservice is backed by an independent storage service, in this case Cloud SQL, for PostgreSQL instances in a decentralized management system. So they're using different node pools to spin up containers, and then those containers are going to run on-demand queries to these databases that are in PostgreSQL. Now, this is an example where the Microsoft SQL Server Management Studio can provide a sensitivity level and a sensitivity label, and to label different columns and different data as sensitive and confidential automatically, and classify that data for different compliance and GDPR compliance and so on. So this is used for data discovery and classification, and this is all done with SQL code that's run to create and store these classifications on the fly. Here's another example of Kubernetes and different pods that are being set up, where an end user from different locations in the globe are connecting to an HTTP ingress load balancer, and then connecting to different regions or zones for low latency. And there is an SQL, Cloud SQL instance there, which is a managed database system with high availability. And finally, there is a different type of SQL for big data. So there is Spark SQL and HSQL, which is Hive SQL, which is used for querying data warehouses and big table and data that's produced by Hadoop and MapReduce. So we're talking about petabytes of data here that are being consumed either by batch or stream, and that data goes into, in this case, the Amazon's EMR, which is Elastic MapReduce, which stores data into a warehouse, and then we use different SQL methods for either ETL or just for analysis and doing data science type calculations and visualizations.